Today, let's go over a really fundamental binary search. It is literally binary search question. This is part of the grind 75 list, and it's an easy question. And obviously, it's very useful. You're going to use it in like 100 other questions. So it's great to learn. So a lot of companies are asking it, and yeah, so it's good to solve. It's not a premium question. So if you don't have that subscription, you can still solve it. So cool. So we're given an integer array, an integer list, which is already sorted. So cool. So we don't have to spend more time sorting it in ascending order from smallest to greatest. And we're given another integer of target, and we want to just write a function, a binary search, to quickly search as to whether target exists in nums or not. If target exists, then return its index. If it doesn't exist, then return -1. And the kicker here is you must write an O of log n time complexity instead of O of n time complexity. So for example, the easiest way to do this would just be to go over nums, the index and the value. If the value is equal to target, return I. If never true, then return -1 once we've iterated through all of the elements and we never find target, right? But that's not log of n, that's O of n. Instead, a better way to do this would be to use binary search. So you already know the array is sorted, so let's define two pointers starting at ends of both arrays. So let's take this array as an example. Let's say we're looking for 9. So cool. We're going to start our left pointer here and our right pointer here. And we're going to define our midpoint, which is, in this case, since the array is of even length, it's going to be 3, because the way it works is indexing is 1 less than the length. So if we're exactly in the middle, then we just want to use this value. It doesn't really matter. You can also use this value. And we're going to ask, is 3 bigger than 9? 3 is not bigger than 9. 3 is less than 9. So there's only one thing to do, which is to close the search space for the left pointer. So next iteration, we're just going to do the same thing and ask the same question. So left is here, right is here, mid is here. And we just happen to have found the target with mid. And so we just return. We don't do any more searching. In cases where we don't have a result, we're just going to get to a point where right and left are going to be at the same thing, are going to be crossing. And at that point, the binary search terminates and we can just return -1. Hopefully this made sense, because the idea is that we're throwing away elements to the left side because they're already sorted, because we're looking for a bigger number than the current one, and we already know the elements to the left are going to be less than, so the result cannot be in the left side, so we're just going to throw that half away. And vice versa for the right side. If we're looking for a smaller number than 5, we know the result's not going to be here, or anywhere to the right side of the array in this case. Cool, so now let's actually define our pointers. And we want to use equals here, because equals, if the result just happens to be the last element, it's going to be O of n. So we don't want to miss that in the worst case. So let's define our mid. These are indices. And now let's ask if nums of mid is equal to target. If it is, cool. Now we just have to return mid, right? Because mid is an index here. Mid is an index, so we want to return the index, not the value itself. And then in this case, the binary search would terminate because we found it. In the case where nums of mid is less than target, right? In this case, nums of mid is less than target, so now we have to close the left search space. So left equals to mid plus 1. So left moves from the 0th index to the 3rd index, because mid was 2, right? 2 plus 1 is 3. In every other case, well, there's only one other case. If nums of mid is greater than right, then we want to close the right search space, right? If we're looking for 4 and we look at 5, then we want to close the right search space to this 3. Right, we're going to make either or decision. We're not going to make both decisions, right? And at the end, if we don't find anything, right, this is eventually going to execute if we find a result. If we don't, then we return -1 as stated in the instructions. And this is going to be log of n in most cases. And as you can see, it's much more efficient. And yeah, this is the power of binary search. Hopefully this helped, and stay tuned for more content. Thank you for watching.